So what to say about this class? The purpose of this class is to give you additional instruction in what's happening in your Ashley class. I'm assuming everyone is in Tim Lewis' 17C class, because I think that's the only 17C class. We'll talk about the syllabus. Really, the only thing you need to know is if you actually registered for the class by signing up with the CRN, you have to attend in person, because the only grading basis for this class is attendance. You didn't sign up with the CRN, you don't have to come at all. Obviously, I think you should come because I think that's the best way to see what's happening. But you're also welcome to attend via Zoom or watch videos later in class, later after class. You're welcome to ask questions. Certainly, it helps if you do have questions to ask. I imagine we'll probably talk about level curves today, because that's probably what you're starting with, or I should say functions of two variables and level curves, which is not as bad as it might sound. We'll scroll through the syllabus here, see if there's anything that seems worth mentioning, and then we'll start talking about some math. Yes. So let's look here real quick. It's always the least fun part of the class, but we should go over it. So let's see here. You're encouraged to come in person. You can also come via Zoom. The best way to reach me is via email. Oh, by the way, I'm James, because I didn't say that already. Please just call me James. You can call me Mr. Parmenter or teacher or something else, but James is what I like the best. Emailing me is the best way to get a hold of me. You can also come by my office or find me in my office hours, which are listed here. Take a look at those real quick. My office hours are Mondays and Wednesdays from 11 to noon in Math Drop-In, Tuesdays and Thursdays right after this class, also in Math Drop-In. Math Drop-In is in the lower level of Shields Library, in case you haven't been there. And then Mondays, Wednesdays, and Fridays from 2 to 3 over in CAD, which is in the South Silo, room 270. It's South Silo is like pretty close here, actually. And those office hours start, the ones in CAD start next Monday, and the ones in drop-in start the Monday after that on October 6th. Speaking of drop-in, it's open Mondays through Thursdays from 10 to 5 and Sundays from 3 to 7 p.m. Welcome, come on in. And those are right there. They're also in the other place we'll look at in a minute here. As far as grading goes, the only thing you really have to know is if you registered for the class, you'll either get a pass or no pass at the end of the quarter. Passing is based on attendance. You have to attend 70% of the classes, which is like 14 of the classes, I think, is what I wrote. Yeah, 14. 14 out of 20 is 70%. If you're not enrolled in the class, the grade you see on Canvas does not matter at all. So please don't ask me why you're failing if you're not enrolled in the class, because you're not enrolled in the class. It doesn't matter what your grade is. What else? There's a lot of things there about being enrolled. Yeah. I tend to get a lot of questions about, I'm failing the class. Why am I failing the class? Is because you're not, because like your grade doesn't matter. So usually it's the other classes, people like 17A or people who are just starting out, like, what's going on? Okay, that's what's going on. If you happen to attend in a different way, either via Zoom or by watching the video at a later date, I will ask you to fill out this form right here, which is not too terrible. Just your email, your ID number, your name, the class you're attending, how you attended, and importantly, the date that the class would have met with the appropriate year, please fill in. Otherwise, it's challenging later to sort things. The reason I ask for this is because part of my job is to collect data on the number of students I serve, and this counts for that and helps us get better funding later on. So please, if you do attend a different way, fill out this form. It's not that terrible. I mean, it will help us continue to get the funding we need to provide the services we do. What else? There's no makeups for in-person class. So if you're actually enrolled in the class, you do have to actually come in person on the day class meets. What else about this class? If something outside of class is impacting your success, please don't hesitate to talk with me about it. I'm happy to be helpful, want to be a resource, happy to change things I'm doing. My best example of that is one time a student said the pens I were using were too thin, like they just couldn't see what I was writing very well, so I started using a thicker pen. So if you have feedback or something I can be doing better, maybe talking a little bit slower, which I often remind myself to do, let me know and I will try to make those changes. What else? Something said that makes you uncomfortable, talk to me or someone about it. I don't anticipate that happening. So yeah. But if it does, please, I don't intend anything offensive. Our class is here. You're here at this time. That is the wrong time on there. One, so we actually meet, though, yeah, that is definitely not the right. Whoosh. Oh, hope nobody read that and this is going to show up at 1 o'clock. So let me, while we're here, let's just fix that real quick. Sorry about that. What happened almost assuredly is I copied the syllabus and pasted from last time I taught this class and forgot to change some of the times. We meet from 12:10 to 1:40. 1:30. 1:30? 1:30. Yeah. My office hours start at 1:40. Let's see what else here. So 12:10 to 1:30 is when we meet here at this place on these days. Most of class will consist of me showing you examples. I might have you do some work together or individually, depending on what we're doing. I do have a handout to that end that I think we might start with. Come to class prepared to work on math. That's kind of the whole deal, right? The way you're going to learn it. I mean, you can watch me do a lot of math, but really, in my opinion, you're going to learn better if you do some problems on your own as well, or at least in the context of this class. So really, the learning happens when you try doing the math yourself or with people. If you have any accommodations, that's great. I'm happy to accommodate you, but also this class really doesn't have anything that needs accommodation. There's no exams, there's no homework. There's really just me showing you math and you may be doing some math in class. But if you have an accommodation that you would like me to accommodate, I'm happy to. Like if you want to record the class on your own or the audio, that's totally fine. I am also recording the class and we'll post it, but you're welcome to have that for yourself. Zoom, people know how to use Zoom at this point. Some notes about the class. It is so if you are enrolled, it's worth 1 workload unit, which means that unit counts towards being a full-time student and financial aid purposes, but does not count towards graduation. If you need a unit, you should certainly enroll. If you don't need a unit and you think attendance might be an issue, you're welcome to disenroll and get added back to Canvas and still have all the same access. It doesn't really matter to me. Each unit is connected to the other stuff. You should be your students. You know what you're doing. You should be spending much time doing your math homework and other mathy things. As far as where else you can get more help, my office hours, the AATC tutoring in drop-in tutoring, as well as I think you can also make individual appointments. Let's see, we can look here. Yep, you can make individual appointments on Oasis with other student tutors. And then each other. You are all your best resources, in my opinion. You should get to know. In fact, why don't you take a few minutes? I'm going to use the restroom. You should all introduce yourselves to each other. I'm going to go pee. All right, now that's right. Okay. Yeah, so syllabus, whatever. The place you'll actually find anything useful that I will post is in the modules, which will be the homepage eventually. Let's look at the student view so you see the things you actually see. So here you'll find some useful links as far as the attendance form I mentioned, my office hours, my playlist for this class the last like 3 times I've taught it. So you can look at old videos if you want to, but it's really just me teaching the class. So it might not feel super easy to navigate, but they are labeled pretty well. So if you're looking for another video on, say, optimization or I don't know, some other topic, you can look through there. My website is not useful at all. Grant's website is super useful. You should all, if you've been at UC Davis before this quarter and have taken math, you've probably been referred to this by one of us. But it has lots and lots and lots of great handouts as well. Nope, not as well. I'm about to say something that's a lie. There's a final review. Okay. But there's really great, like basically class notes as far as how you would, examples of these kinds of things. I won't lie. I often use these notes as inspiration for what I'm going to say in class because they're good examples. Back to the modules. What else do we have here? The 17C syllabus from the math department, in case you want to look and see what's coming your way. All the different things. So chapters 9, most of 10, and 12. So, and really, I'll say chapter 9 is all about like functions of two variables and kind of all the things. It's kind of like most of the things you did in 17A with functions of one variable. And what have we got here? Limits, derivatives, tangent planes as opposed to tangent lines, the chain rule, implicit differentiation, derivatives, but now directional derivatives, which are a little bit different. Maxima and minima, those are all things we did in 17a, just in the context of a function of one variable. So now we're going to extend that to two variables. And fortunately, a lot of it feels like a very natural extension. Like you'll be like, oh, this example seems very similar to the thing we did in 17a, just with now another variable tacked on, kind of. We will talk about double integrals as well, which is kind of feels like it's just kind of wedged in there because it's not in the textbook. So we'll have some extra material. Oh, I will say, assuming that Professor Lewis does cover that. I feel like he usually does, but I'll certainly make sure I keep track of what he's doing so that I'm not like covering stuff that he's not doing in class. Which will be easy in that there's only one instructor for the class, so it won't be hard to like be like, oh, you guys are doing it and you guys aren't. So and then chapter 10 is where things get a little more interesting. This is when we're going to come back to talking about 2x2 matrices and using those 2x2 matrices to solve a system of linear differential equations. So certainly the stuff you learned at the end of 17b, like how to find the determinant of a matrix and the eigenvalues and the eigenvectors of a 2x2 matrix, is very, very, very pertinent. I highly encourage you to review that material before we get to chapter 10 because we're going to be doing that. We'll review it also, but like you want to make sure you're ready for that when it comes. And then chapter 12, we take a whole different, like let's kind of totally switch gears. We stop doing all the stuff we've done. We start talking about probability and counting things, which feels very kind of disjoint, but there is good reason for it. There is lots of biological examples of these probability things. So that's why this material is there. But it can kind of feel not super connected to the rest of the material. Back to the modules. See what else I have in there. Your exam dates, in case, I mean, they're also on your instructor's website, but there they are. We'll get back to this later. Other ways to find eigenvalues of 2x2 matrix. And then some links for graphing things. Hopefully you've played with Desmos before, but if you haven't, you should. 3D Desmos also super useful, especially for this first beginning like chapter of the class. Being able to actually visualize and see the three-dimensional graphs that we're talking about, I think is very helpful. Even if you're not asked to graph something, I would still encourage you to actually plot some of these graphs on 3D Desmos or 3D GeoGebra to help you kind of see what's happening. I'll probably use some of that today or on Tuesday to kind of show you. Oops, come back. And then there was something else. These other graphing things are when we get to the chapter 10 stuff and talk about like direction fields and plotting like the solutions to a system of differential equations. And yeah, these are both kind of the same. There's a worksheet here, which we'll talk about. And then in case you need it, the chapters of the textbook. So if you don't have the textbook on you or just want to reference them, I will point out these are not like, what's the actual textbook you get delivered to you electronically is not easy to navigate, I feel like. Like you have to scroll to the bottom of the page and click over. These are just PDFs. You can still just scroll through them very easily. So I prefer to use these than the actual textbook that is online personally. Yeah. All right, I think that's all the things I wanted to say about the syllabus and the modules. So let me pause for a minute and ask you all if you have any questions. I will be asking you to fill out your name on the sign-in sheet. You will, if your name isn't on there, just write it in. What else? Yeah, yeah. I think I think it's going to be worthwhile for us to work through this handout that I have posted. So we'll do some of this together. Ask themselves on their own, or leave it, we can go later. All right. Couple things as well. So I will try to write legibly, which I'm usually pretty good at. But if you have questions about something I've written, don't hesitate to ask. Also, I usually sometimes I end up getting like kind of like sometimes I'll scoot the paper down and be like writing down here where you can't see. Just let me know. Hey, James, you're off the screen. Um, yeah. So let's look at this handout because although most of these questions probably seem, thank you, like you might have seen them before, these are things that you want to be able to do relatively rapidly. So let's go ahead and write some things down here. Pens, new pens. So this is Co-17C. Today is September 25th. So let's look at the handout. You can already tell this one's dying. So the first few problems here are just graphing some lines. I'm going to do two of these, so I want to find a couple things. So first of all, if I want to graph the line y equal to 3x plus 6. To do this as quickly and as efficiently as possible, you should plot 2 points, specifically the x-intercept and the y-intercept. The y-intercept, we're going to set x equal to 0. We're going to get y equal to 0 plus 6. So we get 0 comma 6. For the x-intercept, we're going to set y equal to 0. We're going to get 0 equal to 3x plus 6. We're going to solve for x. Negative 6 equals 3x. Negative 2 is equal to x. So our x-intercept is negative 2 comma 0. Okay, pen. Maybe I'll actually remember to throw it away this time. So then we're going to plot, or sorry, we're going to graph this thing. We have the x-axis, we have the y-axis. And then I don't, like if I'm doing it this way, I don't want to make a whole bunch of marks because that's really not necessary. It doesn't really help whoever's looking at your work understand any better what you've done. So I'm trying to draw the graph that goes to the y-intercept of 6 and x-intercept of negative 2. So I'm going to kind of just guesstimate it. And actually, before I label anything, I'm just going to draw it. That's about right, close enough. And I'm going to label this as 0 comma 6, this as negative 2 comma 0. Looks pretty decent. In a similar way, let's look at E. This was A, by the way. So looking at E, which is to graph, again, the line 6x plus 4y equal to 12. If you're only asked to graph this line, there's no good reason to solve for y, in my opinion. I can find the intercepts just as easily as before by setting each variable equal to 0 to find the other intercept. So if I set x equal to 0, I'm going to get 0 plus 4y equal to 12, and y is going to equal 3. So I have a y-intercept of 0 comma 3. If I set y equal to 0, I'm going to get 6x plus 0 equal to 12. Divided by 6, I'm going to get x equal to 2. I have an x-intercept of 2 comma 0. X is 2, y is 3, so it's something like this. That might not be perfect, but I don't care that much. There's my graph. Hello, welcome to Co-17C. We're just going over some of the problems on this handout. You're welcome. So graphing lines should be relatively easy. It is important to do them, to be able to do them relatively quickly, because when we start getting to the stuff in chapter 10, we do end up graphing a lot of lines to help us see the behavior of the system of linear equations. So that's kind of looking more towards the future. The next problems are more actually chapter 9 material, or at least they are problems that are with an eye towards what we're going to be doing in chapter 9, which is some functions of 2 variables. So let's actually look at some of these problems from problem 2. So yeah, so let's look at 2b. We have the following equation: x squared plus y minus 2 squared equal to 9. And we want to graph this circle. We know it's a circle because it's written in the usual way a circle is written. X plus or minus something squared plus y plus or minus something squared equal to some other number squared. So here we can see that the center of this circle, by the way, the center of a circle is not a point on the circle, right? The circle is all the points around the center. The center is important, but not actually on the circle. The center, I always think of as the values of x and y and z if we're talking about a sphere. But for a circle, it's the values of x and y that make the left-hand side of this equation equal to 0. So x needs to be 0, y needs to be 2. And again, I'll point out, if you plug those in, 0 squared plus 0 squared is equal to 0, which isn't equal to 9. That point is not a solution to the equation, which is fine. So our center is the point 0, comma 2. Our radius, again, if the circle is written in this standard way, our radius is the square root of this number over here. So our radius is the square root of 9, which is equal to 3. Sometimes we want to graph circles, especially when we're talking about the things we're about to talk about in chapter 9. Papers. Let's see. Let's try and make a convenient pile of my papers instead of just throwing them all over the place. Much better. Okay. If I was drawing the circle, I would probably do it by first plotting the center at 0, 2. Here I am going to make some marks to try and make it look decent. And then I'm going to go 3 in each direction. So up 3, to the right by 3, down 3, and to the left 3. And I'll do my very best job to try and draw a circle that looks halfway decent. Oop, quarter of the way decent. Well, that part got a little bit out of bounds there, but it still looks pretty circle-y. And I will say here, but I won't actually do more than that. But for the next one, x plus 3 squared plus y minus 4 squared equal to 25. In fact, why don't you all write down what you think the center is and the radius? Yeah. And don't worry, this is all going to relate to the stuff we're doing with functions two variables in a minute. So, seeing the circle written in the standard way, it looks like the center is going to be an x coordinate of -3 and a y coordinate of +4. And the radius here is going to be exactly the square root of 25, which is 5. Just an interesting fact here that I'll point out, if you graph this circle with its center and radius, the circle actually does go exactly through the origin. In fact, instead of me trying to graph it, I should show you what the graph looks like, because again, I think it's worthwhile. So I always try and look over there when I've got it right here. If I was to graph this circle, x plus 3 squared plus y minus 4 squared equal to 25. Check it out. It exactly goes to the origin. And it's really because 3, 4, 5 is a Pythagorean triple, right? If you look here from the center, let's graph the center here at -3, 4, right? So from here to there, why don't I just plot that point as well? That distance is exactly 5, because if you go over 3 and up or down 4, 3 squared plus 4 squared equals 5 squared. So that's kind of an interesting fact about the circle, that it happens to have a point exactly on the origin. But really where I want to go with this is the next part, which is to talk about how we use circles to help us find domains of some functions of two variables. So let's look at a totally kind of different thing. I want to graph, and I'm just looking at, I've turned the page, now I'm looking at problem 3. Let's graph the circle x squared plus y squared equal to 9. So I want to show you a few things. Let's refocus here. There we go. So there's the circle x squared plus y squared equals 9. Totally great, totally wonderful. What I really want you to see though is what happens when you, instead of having an equality like this, where the circle, or I should say, the solution to that equation, x squared plus y squared equal to 9, is every point on that circle. So 0, 3, 3, 0, -3, 0, root 2, root 7, right? All sorts of points are on that circle. But what about if we look at the inequality, x squared plus y squared less than or equal to 9? We get all the points inside the circle. Or what if we had just less than 9? See how it's slightly different? So less than or equal to 9, you get the full inside of the circle as well as the boundary. Whereas if it's just strictly less than 9, we no longer get any of the boundary points, right? Because if x is 3 and y is 0, that's no longer a solution to this inequality, right? 9 plus 0 is not less than 9. It's equal to 9. So hold on to that. On the other hand, if we go the other way, if we look at the inequality where x squared plus y squared is bigger than or equal to 9, we get all the points outside of the circle and on the circle. And similarly, if it's a strict inequality, we no longer get the boundary. We just get all the points outside of the circle, but not including the circle itself. So the point here is that, yeah, let's get to some of the points. I feel like I've held off on the point for a while here. The point of a question of a graph like that is looking at functions of two variables, we're going to be asked to find some domains of functions of two variables. For example, for f of x comma y equal to, say, the square root of, let's change up a little bit, 16 minus x squared minus y squared, what's the domain? Well, fortunately, the usual sort of domain rules apply in that we can't divide by 0, we can't take the square root of a negative number, and we can't take the logarithm of 0 or a negative number. So when we have a square root or any even root, we're going to have to say that those insides, that argument has to be greater than or equal to 0. So to answer this question, we're going to say, cool, the argument 16 minus x squared minus y squared had better be bigger than or equal to 0. We don't want to just leave it that way. And I'll say this a few times, I'll say it right now. When you're trying to find the domain of a function of two variables, you want to look for one of two things. You either want to look for a y you can isolate, or an x squared plus y squared you can isolate. Those are the two things that usually come up. So if you see an x squared plus y squared, or a negative x squared minus y squared, basically an x squared and y squared that have the same sign on the same side of your inequality, you want to keep those together. So I would much rather rewrite this, bringing positive x squared and positive y squared to the right-hand side as 16 is bigger than or equal to x squared plus y squared. And I'd probably actually prefer to have rewritten it as x squared plus y squared less than or equal to 16. Same thing, I'd just rather write the variables on the left than the right, but it doesn't really matter. So great, there's our domain, but that doesn't really tell you a whole lot. Now, sometimes people will ask you to express the domain as a set of points, and it's nothing more than what we've already written with a few extra pieces. So here's how you write the domain, which isn't really going to help us a whole lot, but I'm going to tell you anyway. People might ask you to. So the domain here is going to be the set containing every pair of x's and y's, pair of x, y's, every pair of points, x comma y, such that the x and y satisfy this inequality. So we want all the points where x squared plus y squared is less than or equal to 16. Here's how we do that. Or I should say, this is the answer, but it's not a very satisfying answer in my opinion. If I was asking this kind of question on an exam, I would also ask you to graph the domain, because I think that is the more useful piece of information. I wouldn't be surprised if Professor Lewis also asked you to graph the domain, although I'm not 100% sure. So if I was going to graph this domain, here's how we graph the domain. First, don't graph the inequality. Graph the equality. Even if it's a strictly less than or a strictly greater than, we want to graph just the equation x squared plus y squared equal to 16. Now, one thing to note, if it's a strict inequality, a less than, not a less than or equal to, you want to make your graph dashed because you don't want to include the graph. If it's a less than or equal to or greater than or equal to, then you do want to include the graph part of it, the equation, the equation of the graph of the equation. There's no other words to say here. You want it to be solid to indicate that you're including that piece. So here, since it's a less than or equal to, we're going to include the boundary, meaning we're going to graph that circle as a solid circle, a solid boundary. So circle is not too bad to graph. It's the circle centered at the origin with a radius of 4. I say it's not too bad to graph the circle before I try to graph it. Let's see how well it goes. So I want that to be a solid circle. Ugh. Usually I'm a little better at graphing circles than I am today, apparently. Sorry. Okay. So then usually what happens is when you have an inequality like this, you get everything on one side of the boundary. For a circle, it's either going to be everything inside the circle or everything outside the circle. And the direction of the inequality sometimes feels like it tells you what's going on. Sometimes it feels like it's counterintuitive. So here's what I would suggest. Test a point. Test some point that's either inside the circle or outside the circle. So I'm going to test an outside point first. So let's say we want to test this point here. Let's test 5, 0. So if I test 5, 0 in the inequality, in x squared plus y squared is less than or equal to 16, it's not going to work out. 5 squared plus 0 squared is equal to 25, and that is not less than or equal to 16, which means this point is not in the domain, which means everything on this side of the boundary is not in the domain. Or alternatively, we could have tested a point inside, like the point 1, 0 or 1, 1. When we test 1, 1, we see that 1 squared plus 1 squared, which is equal to 2, is less than or equal to 16. So this point and all the points that are on the same side of the boundary are part of the domain. So our boundary graphically is everything inside the circle and on the circle of radius 4 centered at the origin. So to break it down, when you're finding the domain and you want to graph it, you graph the equation, and then it's either everything on one side or the other side of the boundary, as long as there's only kind of one equation. Sometimes you have other weirder things that happen, but most of the time it's kind of like this. Oh, Let's look at another example. When I start talking about function of two variables, I always prefer to start talking about domain because it feels to me like a natural place to start. We'll get to level curves and what some of these graphs look like in a minute here. Yeah, and we'll come back to some of these examples to see what they look like. So let's look at another one. Sure. Yeah, that'll be fine. Let's say our function is g of x comma y equal to 1 over, 1 over is not what I wanted. Sorry, scratch the 1 over. Oh, no, I can fix it. 1 over the square root of x squared plus 3 minus y. And again, we're just finding the domain at this point. Not even talking about the range, although we could. So to find the domain here, we actually have kind of two things in play. Thing one, we can't have a square root of a negative number or 0. Oh, sorry. We can definitely take the square root of 0. What's the square root of 0? Right. We can't take the square root of a negative number. However, in this case, if we did end up getting 0 inside the square root of 0 is 0, but division by 0 is an issue. So in this case, we're going to have a strict inequality where x squared plus 3 minus y has to be strictly greater than 0. I don't have an x squared and a y squared with the same sign. So in this case, instead of trying to isolate x squared plus y squared, I'm going to try to isolate just a y. I'm going to bring the y over to the right-hand side, I'm going to rewrite this as x squared plus 3 is greater than y, or y is less than x squared plus 3. Either way is totally fine. So then I'm going to write the domain, even though it feels unnecessary. My domain is going to be the set containing all x comma y such that this inequality is true. And really, writing this inequality in any way you want to is totally fine. You could have left it like x squared plus 3 minus y is greater than 0, or like this. I just want to point out, like, there's really no work being done here, right? We found the inequality that tells us what the domain should be, and then we literally just wrote all points where that inequality is true. And now we're going to do the thing that's actually some work, is we're going to graph it. So we're going to graph the domain. And the way we're going to do that is, again, by first graphing the equation. So we're first going to graph y equal to x squared plus 3. And since it's a strict less than or greater than inequality, right? We don't want equality here. We're going to graph it using a dashed line, or a dashed curve using dashes, so that we're not indicating that we want to include points on the curve. Okay, so we're going to graph y equal to x squared plus 3. That's just a usual parabola shifted up by 3. So 1, 2, 3. It doesn't have to be very good. Like, I mean, we could plot more points, but I really don't want to. I'm just going to graph the usual kind of parabola. My vertex at 0, 3. There we go. And now we just have to figure out which side of it we want. So we need to pick a point on either side. So be careful. Don't pick a point that's on the parabola, right? Don't pick 0, 3 or 1, 4 or any of the points that actually are on the parabola. Pick something like 1, 1 or 0, 0 is probably even easier. If we pick 1, 1, let's see. So we plug that in. Is it true that 1 is less than 1 squared plus 3? Yay or nay? Yeah, right? Definitely, right? 1 is less than 4. That checks out. Yay. What does that mean? It means that that point is a point we want to include. But that also means then all the points that are on that side of the boundary are also points we have to include. So our domain is everything below this parabola. So all of everything out here. But none of the points up in here. I will also point out, you can totally see this on Desmos if you graph these things on Desmos, which again, I think is kind of neat. So if I graph the inequality, y is less than x squared plus 3, it totally shows you which part you want, everything below the parabola. So certainly if you're finding domains like this and you have to graph them, not a bad idea to check your work using Desmos. It's totally allowed, right? Like you're allowed to use all the tools at your disposal. You should use them. They're really helpful. Let's go back here. Let's see. What else do I have on this hand that I thought was kind of important? Sure. No, that was kind of it for the most part. Oh yeah, totally. So yeah. So certainly making sure you kind of understand how circles work and how graphs work, because we use them to find domains, and also how to graph lines relatively quickly, I think is important. That said, let's kind of continue on with these functions of two variables. And yeah, and we'll talk about level curves as well. What time is it? What time did we get? I might need to end class a little bit early because I have to deliver more today. So we might end a little bit early today just because I need to hit the road at some point. But let's go ahead and talk about functions of two variables more generally. So functions of two variables. And kind of the things we do with them. In fact, I think it's probably worthwhile to go back to the first example we started with. So let's take a closer, more in-depth look at f of xy equal to the square root of 16 minus x squared minus y squared. whose domain we already saw was domain. I'm going to write it this way. It was all points inside and on the circle of radius 4, centered at the origin. So x and y are allowed to be any values that meet that condition. So like 0, 3, 1, 2, stuff like that. But we might want to try to actually graph this thing like in 3 dimensions. So how do we graph this? This 3-dimensional surface. Well, there's lots of techniques. Typically, what we usually do in class like this is we graph what are called the traces, which we'll get to in a minute, and some level curves. So the traces, I should back up a little bit. I feel like I'm being a little ahead of stuff. So when we graph things in 3 dimensions, we have a 3-dimensional coordinate plane. So typically I draw it like this, where I think of the positive x-axis pointing out towards you, the positive y-axis pointing to the right, and the positive z-axis pointing upward. Some people draw this kind of tilted a little bit, where the x-axis and the y-axis kind of look more like they're pointing this way, as opposed to, like I'm drawing it, I'm imagining it more like this, where the x-axis is this, and the y-axis is this. Obviously, I can't actually draw in 3 dimensions, but some other people draw it more like this, where the x-axis kind of points to the left and the y-axis kind of points to the right. Either way is fine. I'm just doing like this, and my drawing skills are mediocre to not too terrible, but I don't want to try and change it because it would look way worse if I tried to do it the other way. So what we're going to do is we're going to draw what's happening in each of the 3 coordinate planes. So we're going to look at what's happening in the XY plane. I should say, we're going to look at the traces. So in the XY plane, that's where z is equal to 0, because you haven't gone up or down. We're going to look at the XZ plane, where y is equal to 0, because you haven't moved left or right. And we're going to look at the YZ plane, where not surprisingly, x is equal to 0. It's kind of like in 2 dimensions, how if you're looking for your x-intercept, you're setting y equal to 0, because you're trying to find out what's happening on the x-axis. You haven't moved up or down. And when you're finding your y-intercept, you're trying to figure out what's happening on the y-axis. You haven't moved left or right. Same idea now, except we have an extra dimension. Yes. I might. That's it. Believe it or not, that's a y. But yes, I wrote it terribly. That's the YZ plane. Yeah, no, but fair question. So right, if so also I'll often refer to the room as kind of like a 3-dimensional coordinate. I should say in this room, I like to say we're in the first octant, meaning where that corner over there is the origin. This line here is your y-axis on the floor. That line there is your x-axis pointing out towards you. And that line there is your z-axis pointing out. So we're in the octant, the 1/8 of 3-dimensional space, where the x, y, and z are all positive. Below us, z would be negative. Behind us, x would be negative. That way, y would be negative. But we're in the room where everything is positive. We're so positive. Something else I want to say. So the XY plane is the floor. The YZ plane is this wall. The XZ plane is that wall. The floor, Z is equal to 0, right? You haven't gone up, you're on the floor. This wall, X is 0. I haven't moved forward at all. That wall, again, from the origin, on this wall, Y is 0 because I haven't moved right or left of the origin, but I can move in the X direction all that I want, or the Z direction all that I want. That's why it's the YZ plane. So to find the traces, we're going to do the easy thing. We're just going to set each thing equal to 0. So I will also point out that this particular one the XY plane, this is also a level curve. So again, I know we haven't really talked about yet. We're going to get there. So I set z equal to 0. And again, not again, maybe I should point out that just like in 17a, when we talked about the function being like f of x equal to x squared, f of x was a stand-in for y, or y was a stand-in for x. Same kind of idea here. F of x, y, we also think of as your output z. Just like for something like, sure. Similar to how if I was graphing like f of x equal to x squared plus 1, I would also say y equals x squared plus 1. Same kind of idea. So we're going to use z and f of x, y pretty interchangeably. So for my xy plane, my z is equal to 0. So I'm just going to rewrite this equation with the left-hand side z equal to 0. So I'm going to get 0 equal to the square root of 16 minus x squared minus y squared. And then I'm going to try to graph that, which we kind of already did. So if I graph this, I'm going to square both sides to make it easier to see what's happening. I'm going to get 0 equal to 16 minus x squared plus minus y squared. If I add this to the left, I get the equation of a circle. X squared plus y squared equal to 16. So my xy trace, sorry, no, that's right, my xy trace is the circle of radius 4. We'll do the same, oh, sorry. We'll do the same sort of thing for the other two traces. So we're setting, I should have written up here, we're setting z equal to 0. For the next two, next we're not going to look quite as nice. Oh well, that's life. So for the yz trace, we're going to set the missing variable equal to 0. So we're going to set x equal to 0. Our equation now is going to be z equal to the square root of 16 minus 0 squared minus y squared. I'm just replacing x with 0 in my equation, in my original function equation. So I'm going to try and graph z equal to the square root of 16 minus y squared, which is not a very nice thing to graph, but it's not that bad. It's really just the top half of a circle. So to make this easier to see, if we square both sides, z squared equals 16 minus y squared. If we add y squared over here, y squared plus z squared equals 16. That's, again, looking like the equation of a circle. Center is 0, radius is 4. But if we look back at the original, z is equal to a square root. And square roots can only have positive outputs. So z has to be a positive, or I should say a non-negative number. Y can be either positive or negative. So like if y is 0, z is going to be 4. If y is 4, z is going to be 0. If y is negative 4, z is also going to be 0. So we're getting the top half of a circle of radius 4. So here's my, typically when you're drawing the other traces, z is the vertical axis and either x or y is the horizontal axis. This is looking like a semicircle of radius 4. One nice thing about the traces, something that's often nice about the traces is that the xz trace and the yz trace are often very similar, if not exactly the same. That will be the case here. If we look at the xz trace, we're going to set y equal to 0. And we're going to be left with the equation z equal to the square root of 16 minus x squared minus 0 squared, which becomes just z equal to the square root of 16 minus x squared. That's exactly the same as this, just with x instead of y. And when I graph it on the xz plane, it's going to look exactly the same. It almost feels silly to graph it at all, but I will. So also a semicircle of radius 4. I could probably do a little more labeling here. Like I'd be like, that's 4 comma 0. That's negative 4 comma 0. That's 0 comma 4. I suppose technically those should have 3 coordinates. Really, this is 0, comma 4, comma 0, because the x coordinate is 0, and this is really 0, comma negative 4, comma 0, and this is really 0, comma 0, comma 4, but I'm not too worried about it. So after we get the three traces, we can often put these three graphs together on the three-dimensional coordinate plane to then graph the three-dimensional surface. So here's what this is going to look like. So I almost always, if I'm graphing this, like to start out by drawing what's happening in the YZ plane, because that's the plane that's like on the piece of paper, there where there isn't any kind of distortion of what I'm drawing. It's going to look like how it should typically look. So in the YZ plane here, I should just have a regular semicircle of radius 4. That's interesting. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So here's what's happening in the YZ plane. The same thing is happening in the XZ plane, but the XZ plane is tilted, right? It's no longer, if you look here, it's no longer as long as the YZ plane because it's done this, and it looks much, much shorter. So in the XZ plane, these little hash marks get shortened a little bit. In the XZ plane, I have this semicircle. And it's going to go behind here, so I'm going to draw it dash because we're pretending like we can't see it. So there's that semicircle in the XZ plane. And then in the XY plane, we have the circle of radius 4, which is going to go through the points 4, 0, 0, 0, 4, 0, that one back there, which is negative 4, 0, 0, and this one over here, which is 0, negative 4, 0. And we're just going to draw a circle, but it's a circle that's sitting on the ground. So it looks kind of distorted. So there's our three-dimensional graph. And appropriately, it looks like a hemisphere. Hemisphere is, I guess, the wrong word. It's the top half of a, yeah, no, it's a hemisphere. That's the right word. There's different words to use if you're including the interior points or not. Sphere is just like a circle, all the exterior points that are some given distance away from the center. If you wanted to describe all the points inside of a sphere, you would call it a ball. Not quite done with this example. We're mostly done with it. So the other thing I want to talk about here is what are called level curves, also known as contour lines. I feel like there's another word for it as well, or lines of elevation. Essentially, if you've ever looked at a topographical map, you've seen a level curve. It's a line that's representing all the points that are at the same elevation on that map. So we could draw some level curves here. Maybe if I could pick up a pen. So yeah, more paper. So what are some level curves of this function? Level curves of f of x comma y equal to the square root of 16 minus x squared minus y squared. So essentially you're asking the question, what does a two-dimensional graph look like if you were to kind of slice this thing at a certain elevation? So like here it's kind of easy to view. I wish I had an orange with me that I could cut. But like if you essentially had half of an orange and then you decided to cut it somewhere in a plane that's horizontal or parallel to the ground, right, you would get a shape that's probably a circle. Definitely a circle, unless your orange is really deformed. And that's kind of how I imagine level curves, is you're taking your surface. I know the orange is a solid, not just a surface, but you're taking your surface and you are cutting it to see what just the part you're left with around looks like. Welcome to Co-17C. I have a question. Did you read that the class is from 1 to 2 on the syllabus? Okay, so that is my fault. I apologize. I wrote the wrong time. I was worried, so I was like, oh no. So welcome to class. I apologize for making you late. We're talking about three-dimensional graphs and level curves right now. So we just graphed this function, f of x y equal to 60 square root of 60 minus x squared minus y squared, and it looked like the top half of the sphere. And now we're going to talk about what happens if you say, if we're at a height of 1, what does the two-dimensional graph look like, essentially? Well, let's find out. So, to find level curves, you set z, or the function, equal to some number. Now, we're limited in what kind of choices we can make for that number because you can't set the function equal to a value that's outside of its range, right? This, if you look back at the graph, the range is seemingly very limited, right? We don't go any lower than 0, and it looks like we don't go any higher than whatever this point is here, which is probably the point 0, 0, 4. But if we hadn't already graphed it, how would we know what kind of points we could pick? Or I should say, what kind of values we could pick? Well, finding the range, especially for a function of two variables, is always kind of a, what's the way to say this the right way? Guess and check? No, guess and check is not. Oh, I just did something weird. Sorry. Guess and check is probably not the right way to say it. It's a, yeah, okay, I'll say these words. The question you're trying to answer is, how big can this function get and how small can this function get? So the way I usually like to think about this when we're talking about the range is to ask the following questions. What can we pick for x and y to make z equal to f of x comma y 1 as small as possible, 2 as large as possible? It's not the only way to do it, but it's the way I've seen that probably works the best most of the time. So for this function, we kind of already have an idea of how small it can be. Because when you have any sort of square root of some stuff, the outputs have to be non-negative. So the smallest you can ever get with just a square root is equal to 0. Can this equal 0? Definitely. We can certainly pick values for x and y that'll make this function equal to 0. For example, so for question 1 here, we can pick x comma y equal to 4 comma 0. And then f of 4 comma 0 is equal to the square root of 16 minus 4 squared minus 0 squared, which is the square root of 0, which is 0. But we can't get any smaller, right? Just not possible. If you get a square root of a negative number, it's not real. And when we're graphing things, we have to limit ourselves to real numbers. As you might be aware, in 17b, you did talk about imaginary eigenvalues, or you might have talked about imaginary eigenvalues. Imaginary numbers are coming back our way. So when we get to the part of this class where we talk about solving systems of linear differential equations and finding the eigenvalues and eigenvectors of 2x2 matrices, sometimes they will be complex, which will correspond to the system being a spiral. Just so you know. We'll definitely think more about that later, but certainly complex or imaginary numbers are part of this class that you will encounter. A more interesting question, I think, here is for part 2, how can we make this as large as possible? Well, I think rewriting it as f of x y equal to the square root of 16 minus parentheses x squared plus y squared makes it a little easier to see how to make it as large as possible. If I want to make something as large as possible, I usually want to subtract as little as possible. So I would love for x squared plus y squared to end up equaling 0 so that I subtract off the least amount I can, right? Because x squared plus y squared can never be negative. The smallest it can ever be is 0. So if I say, well, it looks like x and y have to be 0 and 0 each, then we're going to say that f of 0 comma 0 is the square root of 16 minus 0 squared plus 0 squared is 0, and the square root of 16 is 4. So that is the largest value for this function. So we would say that the range, unlike the domain, which again, I know some of you came in just now, I'll remind you, or tell you that the domain we found for this earlier was the set of all points x comma y such that x squared plus y squared is less than or equal to 16. Basically, all the points inside the circle of radius 4 centered to the origin. Our range, on the other hand, is much easier to write. It's more like how we write domain and range in 17a. It's just an interval that goes as low as 0 inclusive, excuse me, and as high as 4 inclusive. By the way, welcome to the person who just joined us on Zoom. I'm imagining the person who just joined us on Zoom also probably correctly read the syllabus that class started at 1, but that was my error. Class actually starts at 12:10 and ends at 1:30. So I apologize if you are coming late because of my error. Let's see here. Let me fix this here real quick. But thank you for coming. So the range here is from 0 to 4, meaning if we're going to try and draw some level curves, we can only pick values between x equal to 0, sorry, z equal to 0 and z equal to 4. Can't pick anything bigger than 4 because you can't end up getting the function equal to that. Similarly, we can't pick anything negative for the same reason. So often when we draw level curves, we pick like 2 or 3 values, and then we kind of graph those. So for our level curves here, I should write that out. Level curves. For our topographical map, we're going to pick some entries. So we'll pick z equal to 0, which we already did. We'll pick z equal to 1, z equal to 4, z equal 4. Ooh, let's just do all the integers. Sure, 2. That's probably more than I really want. Z equal to 0, 1, 2, 3, and 4. So I don't really want to do this 5 times, although we could. But here's what people actually do. So let me do one of these. Let's just pick one of them real quick, and then I'll show you the way we do this. So let's say we pick z equal to 3. We plug that into our function, or I should say, if we set our function equal to 3, we're going to have 3 equal to the square root of 16 minus x squared minus y squared. Writing it that way doesn't help me. I don't know what that graph looks like without doing some work. What do I see that's helpful? I see an x squared plus y squared. Technically, I see a negative x squared minus y squared, but you should think of that as minus x squared plus y squared. So if I see an x squared plus y squared, I want to isolate that. So that's what we're going to do. To isolate that, I'm going to square both sides. So 3 squared is 16 minus x squared minus y squared. I'm going to add the x squared and y squared to the left. I'm going to subtract the 9 from the right and get x squared plus y squared equal to 16 minus 9. Or in other words, x squared plus y squared equal to 7. Cool. I know what that looks like. That's a circle centered to the origin, radius of, unfortunately, the square root of 7. So circle, radius is square root of 7. I don't want to do that work 4 more times. More importantly, I don't need to do that work 4 more times. Here's what we're going to do instead. So instead of repeating this work, do this. For some reason, instead of using z, we use the letter c for like a constant we've picked. So we're going to set our function, the square root of 16 minus x squared minus y squared, equal to just some generic constant c, where we know, or maybe we can write down the c has to be between 0 and 4. But really, I don't think you need to write that down personally. And then, just like before, where we had the square root of 16 minus x squared minus y squared equal to 3, we're going to isolate the x squared plus y squared in the same sort of way. So we're going to square both sides. We're going to get 16 minus x squared minus y squared equal to c squared. We're going to isolate the x squared plus y squared. So we're going to get 16 minus c squared equal to x squared plus y squared. Or if you want to write this, I don't think you need to, but you could rewrite it as x squared plus y squared equal to 16 minus c squared. So this is a circle, or I should say it's the equation of the circle. The center is still the origin, right? Because it's x minus 0 squared and y minus 0 squared. And the radius is the square root of this number over here. And then you can do the easy thing and say, we'll just pick the different values that we've already chosen for z up here. So if I plug in c equal to 0, I'm going to get a radius of the square root of 16. If I plug in c equal to 1, I'm going to radius of the square root of 16 minus 1, square root of 15. If I plug in c equal to 2, I get the circle of the center as the origin, and I get a radius of the square root of 16 minus 2 squared, which is the square root of 12, and so on. If c is 3, I get a radius of the square root of 16 minus 9, which is the square root of 7, like we already found up here. And lastly, kind of, I don't know what the word I want to use here is. If c is 4, we get the square root of 16 minus 16 for our radius, so we get a radius of 0. Meaning that circle at the very highest height of our surface is just a point if your radius is 0. Okay, so here's how we would actually draw these level curves. And this is probably where I shouldn't try to draw them because it's just going to look terrible. Instead, let's draw them in Desmos. Because really, that's something that I know about myself is it's hard for me to draw 5 concentric circles or 4 concentric circles. So here's what our level curves would look like. We'd first have x squared plus y squared equal to 16 was the first one, yeah. And then the next one was x squared. I bet there's a better way to do this. Plus y squared equal to 15. Right? See, that would be hard for me. That'd be really hard for me to draw. And then we had x squared plus y squared equal to 12. I know it's kind of boring, but and then finally x squared plus y squared equal to 7. And finally, sure, x squared plus y squared equal to 0, which is just that point in the center there. So this tells us a few things. Now I should point out, I wonder what'll happen if I do that. Let's see. I'm gonna do one thing here just to see what happens. Cool, it doesn't change anything. So normally, when you draw level curves like this, you also label each level curve with how high that curve is, right? We want to know, right? If you just look at this topographical map and you don't know which curve represents which elevation, you don't know if you're coming from the outside going inwards, if you're having to go upwards or having to go downwards. But if we label each thing, and usually I'd actually write it on each curve, but this is the best I can do. Right, this is equal to, I did not like that. I'm a liar. So, okay, fine. So there's our level curves. And then we label each one of them and we can see that, okay, cool. As we go upward, right, from a level curve of z equals 0, where the circle is a radius 4, a little bit higher at a height of 1, circle's a little bit smaller. Height of 2, circle's a little smaller. Height of 3, circle's a little smaller. Height of 4, the circle's a point. And then we could go back to our surface that we drew. Maybe I can grab it here. And actually see. And this is where I would recommend using different colors of pens or pencils if you have them. So here's our bottom level curve here at z equal to 0. And then if we go up 1, bear with me here. So by the way, the way I'm doing this is from a height of z equal to 1, I'm going straight left and straight right to find the points on that part. And then parallel to the x-axis, parallel to the x-axis, back and forth to find that. So I'm going to try and draw this circle here. I should probably draw it dashed. No, I lied. I'm going to draw a solid dash back there. So there's the circle of radius root 15 at an elevation of 1. If we go up a little further, are you here for Co-17C? It's all right. If we go up a little further, here's our level curve at a height of 2 with a radius of the square root of 12. He tries to draw. I should also show you how we do this on Desmos. My drawings start to fall apart. And then finally, the last one at a height of 1, 2, 3, here, there. So those are the level curves that we just saw. And if we were to look straight down from the top along the z-axis, it would look exactly like those circles. So that's kind of that. I didn't do the colors in that order, sorry. But that's the whole idea, right? Is those circles there are just that three-dimensional graph, but the topographical view of it looking downward, which is helpful, right? Because we can kind of decipher what the 3D graph might look like from this two-dimensional representation of, okay, it's this high here, it's this high here, it's this high here, and so on and so on. Yeah. All right. I should probably stop there. We end at 1:30. We can stop. I said I was going to end a little early, but not that early. So call today. We meet again we meet Tuesdays and Thursdays at 12:10, not 1:10. Sorry again to you on Zoom as well. Fortunately, the class is recorded, so if you want to watch what we did earlier, you are more than welcome to once I've uploaded it, which I should be able to do before I take off. So have a lovely rest of your 0th week of classes, and I will see you all next Tuesday. Thanks for coming. Oh, and for those of you that didn't get to sign in the sign-in sheet, please do put your name on this. Also, one of the things to say is, if there are things you want me to talk about in class, let me know. Either in class when you get here, or you can send me an email or write a thing on Canvas. Anything is fine. But if you let me know, you're more likely to get to see the things you want to see.